Now, we are going to start with the next part of the chapter, haloalkanes and haloarenes. We were talking about properties of these compounds. So now, let us start with chemical properties. You have seen the structure of haloalkanes like this. Halogen being electronegative acquires slight negative charge and carbon acquires slight positive charge. So this carbon attracts nucleophiles towards it. This carbon attracts nucleophile towards it. This halogen is also a nucleophile. If some strong nucleophile comes, then this halogen can be replaced, can be substituted. So, the most useful, most important organic reactions of alkyl halides are nucleophilic substitution reactions. Why nucleophilic substitution? Because carbon attracts nucleophile being positively charged and halogen can be replaced. The reaction takes place like this. Nucleophile attacks this carbon and halogen goes out. Halogen may be chloro, bromo or iodo. Now, this is a table which shows some common reagents, some common nucleophile and the products formed. If the reaction is done with NaOH or KOH, then OH is a nucleophile. It comes in place of X and you get ROH. Similarly, from water, OH will come in place of X. Here also you get alcohol. From NaOR, OR dash is a nucleophile which replaces halide. Here NaI, I is a nucleophile. From NH3, NH2 is a nucleophile. So here NH2 comes. If it is RNH2, then RNH group is a nucleophile. Here it is written NH3 because basically lone pair of electrons act as a nucleophile here also and here also. Similarly with KCN and AgCN also. This CN group is a nucleophile. Then KNO2, AgNO2, NO2 group is a nucleophile. With RCOOAg, RCOO group is a nucleophile. From lithium, aluminium hydride, H is a nucleophile, and from metal alkyls, alkyl group is a nucleophile. From these reactions, some of the reactions we will take in detail like this. With aqueous NaOH, you can see X is being replaced by OH. Here X is being replaced by NH2. X is being replaced by hydrogen. X is being replaced by R. X is being replaced by Cn. X is being replaced by Nc. X is being replaced by ONO and X is being replaced by NO2. Now let us come to these two reactions. Here we have taken NaCN, here AgCN, but the product formed in both the cases is different. With NaCN you get cyanide, whereas with AgCN you get isocyanide. Similarly, this pair of reactions. With NaNO2 you get alkyl nitrite, whereas with AgNO2 you get nitro compound. Now what is the reason? This pair and this pair. Here you get the reason. Cyanides and nitrites possess two nucleophilic centers. Such nucleophiles are called ambident nucleophiles. Cyanide is a hybrid of two contributing structures. This here negative charges on carbon. So Nucleophilic center is carbon. This carbon will attack and make bond. And the another hybrid structure is CN, where nitrogen has got a lone pair of electrons, so attack takes place from nitrogen. Now let us again come to these two reactions. In case of NaCN, there is an ionic bond between sodium and cyanide. In aqueous solution in water, CN separates negative charge on carbon. So attack takes place from negative charge of carbon, and so the product is NRCN. AgCN is a covalent molecule. Even in water, CN is not free, so attack takes place through lone pair of electrons present on nitrogen, so bond formed is also by nitrogen. Similar is the case with nitrite. Here also there are two different points of linkage. Nitrogen, negative charge, and nitrogen because of lone pair of electron, and oxygen because of the negative charge. Similar is the case here. With NaNO2 or KNO2 being ionic, they break in aqueous solution, so attack takes place through oxygen. Bond is also formed with oxygen. But with silver AgNO2, oxygen is not free as there is a covalent bond. So attack will be due to lone pair of electrons on nitrogen. So bond formed will also be from nitrogen. This is a very important question. Same question which I have explained just now. Usually this question is asked in exams too. Haloalkanes react with KCN to form alkyl cyanides as the main product, while AgCN forms isocyanides as the chief product. Same question can be asked with KNO2 and AgNO2 also. Answer will be same. Nucleophilic substitution reactions can be carried in two ways. First is substitution nucleophilic bimolecular, S substitution, and nucleophilic, and 2 is for bimolecular reaction. Bi means 2. Here 2 molecules are there in rate determining step. It is a single step. No intermediate can be isolated. As the reaction progresses, the bond between the nucleophile and the carbon starts forming. The bond between carbon and leaving group weakens. Configuration of the carbon under attack gets inverted. This process is called inversion of configuration. The order of reactivity is primary, secondary, and then tertiary. You can see here, this is primary alkyl halide. This is a nucleophile. It is a backside attack. Backside attack is visible only when here the 3 groups attached are small. That's why the order of reactivity of primary is maximum. So here it is a transition state. It cannot be isolated. The bond between OH and carbon is being formed, between Br and carbon is being weakened. Then the OH is being formed and Br goes out. Here it is like an umbrella. This is umbrella and this is the handle of umbrella. And due to the attack of OH, this umbrella gets inverted like the umbrella gets inverted in a storm. You can see here OH group and then the alkyl bromide. OH group comes closer, makes a bond and transition state, then the Br goes out. Second is substitution nucleophilic unimolecular. Substitution nucleophilic unimolecular. Uni means one molecule. Here, rate determining step contains only one molecule. These are generally carried out in polar protic solvents. Protic solvents which contain proton like water, alcohol, acetic acid. Rate of reaction depends upon concentration of only one reactants. It occurs in 2 steps. In step 1, CX bond gets polarized, undergoes cleavage to form carbocation and a halide ion. This is a slow step and is a rate determining step. Carbocation thus formed is then attacked by nucleophile in step 2 to complete the substitution reaction. You can see here it is a substrate. The bond between carbon and leaving group breaks, leaving group leaves. So a carbocation is formed. Nucleophile attacks on this carbocation. This is a second step. It is a first step and you get the product. So for SN2 reaction, as I have explained, the maximum reactivity is of primary and minimum is of tertiary. But for SN1 reaction, tertiary alkyl halides are most reactive, then secondary and then primary. Actually, the nucleophilic substitution unimolecular reaction takes place, is facilitated because of the formation of carbocation. So, the reactivity order depends upon the stability of carbocation. Since tertiary carbocation is most stable, that's why tertiary alkyl halide is most reactive. For the same reasons, allylic and benzylic halides show high reactivity towards SN1 reactions because in both allylic and benzylic, carbocation is stabilized due to resonance. So we can say for SN1, the order of reactivity will be benzyl, allyl, tertiary, secondary and then primary. So you can see here, for benzyl carbocation, you can form 5 resonating structures. For allyl carbocation, you can form 2 resonating structures. So both of them are resonance stabilized. Benzyl being better stabilized, so reactivity of benzyl is greater than allyl even. Then we have elimination reactions. When a haloalkane with beta hydrogen atom is heated, which is what is beta hydrogen atom? The carbon to which Br is attached is called alpha carbon atom, and the carbons attached to alpha carbon are called beta carbons, and hydrogen attached to those carbon are called beta hydrogens. So when a haloalkane with beta hydrogen atom is heated with alcoholic solution of KOH, there is elimination of hydrogen from beta carbon and halogen from alpha carbon. As a result, alkene is formed as a product. Now, because beta hydrogen is involved in elimination, so this is often called beta elimination. You can see this is a nucleophile OH. It takes this hydrogen to form water. Electron pair goes inside to form double bond and Br goes out. We can learn details about both substitution and elimination reaction in further videos.